Hi everyone. Now we are going to discuss about the question number 54, which is based on conservation of angular momentum. We have studied already what is torque and angular momentum. But here we are going to study a specific case of what is conservation of angular momentum. Like here the very first thing is what is the definition of angular momentum? See, the definition of angular momentum is moment of linear momentum. So moment of linear momentum is called angular momentum. That is L bar equal to R bar cross P bar, or L bar equal to M into R bar cross V bar, or magnitude if you consider MV sin theta. But here majorly they will ask questions based on a rigid body rotation about a fixed axis. In that case, how we can apply conservation of angular momentum? So that in case of a rigid body, in case of a rigid body, the angular momentum is I into omega. Now the question is, what is conservation of angular momentum? Then we can understand how to apply conservation of angular momentum. See here, what is conservation of angular momentum is torque tau equal to dl by dt. If there is no external torque, if there is no external torque on a rigid body or system, then angular momentum remains constant. That is, torque tau equal to dl by dt 0 implies L remains constant. So L means I into omega remains constant, implies omega is inversely proportional to I, implies I1 omega 1 equal to I2 omega 2. So just like they can give many examples. See one example, like in case of shrinking in mass of earth, the angular momentum remains constant. Or when a child sitting on swing suddenly stand up, then angular momentum remains constant for the system. So no one is applying any force. He is just standing. So when he is standing, he is swinging means he is moving in rotational motion. There is some moment of inertia, there is some angular velocity. But when he suddenly changes its position with respect to reference axis, his moment of inertia changes. As his moment of inertia changes, omega also changes accordingly. Like before standing I1 omega 1, after standing I2 omega 2, but I1 omega 1 must be equal to I2 omega 2. That is, angular momentum remains constant. In case of attaching or removing mass from a rigid body like ring or disc, so on. So every case, I have given few examples, but in every case, when they are mentioning attaching or removing, they will say like gently, without any external effect. So in that case, you have to understand, you have to analyze on your own that we can apply conservation of angular momentum principle here. So, like that, the formula is very simple. Only thing you need to understand that in the given question, we can apply the conservation of angular momentum principle, just like conservation of linear momentum. There, the net external force is zero means linear momentum remains constant. Here in rotational motion, net torque is zero means the conservation of angular momentum is valid. So let's see few examples based on whatever we have discussed. The very first thing is a wheel of moment of inertia I and radius capital R is rotating about its axis at an angular speed omega naught. It picks up a stationary particle of mass m at its edge. Find the new angular speed of the wheel. See, it picks up means they are not telling that someone is throwing on it. So we have to consider that it is taking one mass and attaching to it very gently. So you have to understand that we can apply I1 omega 1 equal to I2 omega 2 according to conservation of angular momentum, as resultant torque is 0. Now I1 is I and omega 1 is omega naught. Now omega 2 we have to find. What about I2? Now it is a wheel. Wheel means it's just like a disc. Mass m. Now about central axis it is rotating like this. Now once a mass is attached means the new moment of inertia will become, the disk moment of inertia is mr square by 2. I only. Plus this mr square by 2 is nothing but I only. Plus m into what is the perpendicular distance of the attached mass? R. So mr square. R nothing but you can take mr square. Then you can write I omega naught equal to I2 is I plus mr square times omega 2. So this way, once you understand the question, then what is initial value? What are the initial values? What are the final values? Which one they are asking to find? You will come to know. And here also if you see, if you can find out what is the moment of inertia of a point mass or regular body, then only you can apply the conservation of angular momentum. That's why in the entire rotational motion, whenever you consider whatever may be the topic, the very first thing is you should know how to find the moment of inertia. Next. A thin circular ring of mass m and radius r is rotating about its own axis with an angular velocity omega. So one ring is there. It is rotating about its own axis with angular velocity omega. Mass is m, radius is r. Then the moment of inertia ring is mr square initially, and initial omega 1 is omega. Now two objects each of mass m are attached gently to the ring. As I mentioned, they are telling they are attached gently to the ring. The wheel now rotates with an angular velocity. See, actually here one thing they should specify in the question. They attached the rings at the edges somewhere. Otherwise you cannot calculate it properly. So that the distances will become r. Because where they attached, if we don't know, how can we find it their moment of inertia? So that I2 will become the ring moment of inertia same, but small mass moment of inertia mr square plus mr square. So that it will become mr square plus 2mr square. Now, if you take r square common, m plus 2m. Now, as we have taken the formula I2 omega 2 equal to I1 omega 1 implies I2 is r square into m plus 2m times omega 2 equal to I1 is mr square times omega. Now, r square cancel, then omega 2 equal to m omega by m plus 2m. So So this way, you need to take initial and final moment of inertia, then you can apply the conservation of angular momentum principle. Now let's see another question. A boy stands on a freely rotating platform with his arms extended. His rotation speed is 0.3 revolution per second. When he draws them in, his speed increases to zero point 0.5 revolutions. Ratio of his moment of inertia in these two cases is, see here, a boy standing on a freely rotating platform with his arms extended. Now the first case is just like the hands are stretched, extended. Now the angular speed, initial angular speed is 0.3 revolution per second. Let's take the moment of inertia I1. We don't know. Now when he withdraws, see the situation simply it will become like this. Now the new angular speed became 0.5. See here, he stretched initially he was stretching the hands. Now he is pulling back means about this axis is rotating. Now about the axis of rotation, mass came closer. So moment of inertia obviously decreases. As moment of inertia decreases, omega should increase according to conservation of angular momentum. That's why here omega increased. Now the new moment of inertia you consider I2. Then I1 omega 1 equal to I2 omega 2 implies I1 by I2 equal to omega 2 by omega 1, where omega 2 is 0.5, omega 1 is 0.3, so that the ratio will become 5 by 3. Now similarly one more question. A uniform disk of mass m and radius r is rotating in a horizontal plane about an axis perpendicular to its plane with an angular velocity omega. Another disk of mass m by 3 and radius r by 2 is placed gently on the first disk coaxially. Then final angular velocity of the system. Now first one disk is there of mass m, radius r. Then its moment of inertia will become mr square by 2 and the initial angular velocity is omega. Now on the same disk of radius r, now one more disk of radius r by 2, they placed gently coaxially. Now both will rotate with the same, about the same axis only. Then moment of inertia changes. For the first disk already mr square by 2. For the second disk mass is m by 3. R is r by 2. mr square by 2. So that it will become mr square by 2 plus mr square by 2 if you take common 1 by 4. So 1 by 12 will come. So that I2 will become mr square by 2 if you take common 1 plus 1 by 12, that is 13 by 12. Now we don't know what is the new angular velocity. So that we will take I2 omega 2 equal to I1 omega 1 implies omega 2 equal to I1 omega 1 by I2. I1 is mr square by 2 times omega by mr square by 2 times 13 by 12. So mr square by 2, mr square by 2 cancel. So it is 12 omega by 13. So this way, in every question we are applying similar kind of procedure. Only thing object may be different, the question may be slightly different, but the procedure is same and the key role played by in every question is moment of inertia if you observe properly. So that's why you have to first understand how to find moment of inertia. Now one last and final question. A dancer spins about himself with an angular velocity omega with his arms extended. So a dancer spins about himself with an angular speed omega with his arms extended. So now arms again extended just before we have shown. When he withdraws his hands in, his moment of inertia reduces by 40%. So initially he is stretching his hands. Now the moment of inertia is I1, omega 1 is omega 1. That is how much they have given, omega. Now when he withdraws the hands, now the moment of inertia became I2, but they are telling I2 reduces by 40%, means I1 minus 40% of I1. So 40% reduced that of initial value. That means how much it will become? So 60%. So 60 by 100. So that 3I1 by 5. Now they are asking the new angular velocity. See, here also the similar question, but the way of giving the data is different. So the moment of inertia, they said some percentage got decreased. So using that sentence, if you understand, you can make this mathematical equation, then you can solve the question very easily. So that again I2 omega 2 equal to I1 omega 1, where omega 2 equal to I1 omega 1 by I2 again. So that I1 omega by 3 I1 by 5. Again omega 2 will become 5 by 3. So 5 omega by 3. So this is how the simple questions based on conservation of angular momentum they can be asked. And many times they ask the question based on this, like similar questions only. So similar questions I have given as an assignment also. Please just try to understand and try to solve them. So thank you. We'll continue in the next session with the next question. Thank you.